Hey all listeners, this is Prajesh Chaudhary Kondam Guru. In this video, I'm going to present you a very good problem of rigid body dynamics, that of a physics of sliding rod. The beauty of this problem is that through that one situation, we can think of 14 different problems. Each problem in it is a goal thing. So let me explain the setup and we'll try to solve a problem one by one. So here we have this is the rod AB. The rod AB is of length L. Initially, the rod AB is leaning on the wall. This is the wall, this is the floor, all surfaces are smooth. Then what we do, we just give a slight disturbance so the rod starts sliding on the wall and also on the floor. So when the rod makes a angle theta from the vertical at a general movement, we have to find so many things. First of all, we would like to locate the IAOR, instantaneous axis of rotation. We want to find the velocity of the ends. We want to find the velocity of center of mass. We want to find a point on the rod which has a velocity along the length. We want to find the angular acceleration of the rod. We want to find the angular velocity of the rod. We want to find the acceleration of points A, B, IOR and center. And we also want to find the trajectory of the center of mass, center, and also the trajectory of any general point. And finally, that is the very best part of the question, the last part, that at what angle from vertical the rod will lose contact from the wall. So these are the things, and let's try to solve these things. So once again, let me show. This is the vertical wall and this is the floor. All surfaces are smooth, and as I explained, the rod is just given a slight disturbance and the rod starts sliding. So at a general movement, we have to find all those things and that I just told. So we'll try to do one by one. So now, first of all, what is the location of the rod? Location of the IAOR, all right. So I had named the upper end was A and the lower end of the rod was B. Now at this general movement, this rod is at this angle theta. This is A and this is B. The constant of the motion requires that the point A has to move along the rod. So velocity of the point A will be along the rod. So this is say VA. And the point B is allowed to move along the floor. So velocity of the point B is VB. We know that if we know the any 2 points velocity, we can locate the IAOR, instantaneous axis of rotation. Instantaneous axis of rotation is the axis from where CTRM appears to be pure rotational. So when the velocity vectors are not parallel, what we do? We make the perpendiculars at their tails. So, and the point of their intersection will give the instantaneous center of rotation, ICOR, and a line perpendicular to ICOR and perpendicular to the plane of motion is the IOR. So here this is the, I have just drawn the perpendicular at the tail of velocity vectors. So this is the IAOR. Their intersection would be ICOR and an axis passing through ICOR and perpendicular to the plane of motion is IOR. So this is simply IAOR, instantaneous axis of rotation. All right. So that is easy part. And now, angular velocity of the rod when the rod makes angle theta from vertical. So this was the initial position of the rod. Given a slight disturbance, the rod is now at this position. Here it is making an angle theta from the vertical. We just located IOR at this instance is here. Here, this is the IOR. And we know that from IOR motion appears to be pure rotational. So clearly the rod is like this and it is moving like this, so it is rotating. So it will have an angular velocity, and I want to look from IAOR. This is a part of dynamics basically. So we know that if there are no non-conservative forces, external forces do not do any work, the mechanical energy of the system conserve. Forces acting on the rod are the weight and the normal at the ends A and B. The normal are there, but they are not doing any work because displacement is perpendicular to them and gravity is conservative, so their mechanical energy is conserved. So mechanical energy is conserved. So what we can do from the initial state when the rod was vertical to this new state, you can just write apply conservation of mechanical energy. So that is a gain in kinetic energy is equal to loss in potential energy. All right. For the loss of potential energy, what we have to do, we have to see that how much distance the center of the mass of the rod has fallen. So we are assuming the rod to be uniform. So initially the whole mass of the rod is at the middle point here, that is this distance is obviously L by 2. And now suppose the center mass has come somewhere here, and if this is this, so now the new height, this will make angle theta from vertical. MB is L by 2, so that would be L by 2. This length would be L by 2 cos theta. So center mass height has gone from L by 2 to L by 2 cos theta. So loss of potential energy would be mg L by 2 1 minus cos theta. And gain in kinetic energy. Gain in kinetic energy is, initially it was at rest, so there was no kinetic energy. Now whatever kinetic energy, that is the gain. So that would be from, if I am looking from IUR, expression for the kinetic energy would be half I about K would be half I about IAOR into omega square. And from any other point, if I would have to write kinetic energy, I will have to write K is equal to half mvcm square plus half ICM omega square. So I don't want that complexity, so that's why I am looking from the instantaneous axis of rotation. So from this axis, we know this is the center of mass here. About the center of mass, moment of inertia is ml about center of mass and perpendicular to the plane, obviously. Moment of inertia is ml square by 12. And this point, this point, this point, this point, all these points are at a distance L by 2 from center of mass. So about this point, this point, this point, this point, moment of inertia is same. And about n, that is ml square by 3. So about this also ml square by 3, but directly you can also write this is a center of mass and this distance is L by 2. So moment of inertia would be ml square by 12 plus ml by 2 whole square. That will come out to be ml square by 3. So now the gain in kinetic energy is half I is ml square by 3 and omega square. So if I put the make it simplify, so that will become square root of 3g by L. 2 and 2 will get cancelled, m and m will get cancelled, and 1 minus cos theta, and everything will be inside the square root. Alright? So angular velocity we got by the conservation of mechanical energy. And now for the velocity term, I will write in terms of omega, and whenever I'll have to go deep, then I'll put the value of omega. So angular velocity we got, and now angular acceleration. So once again, this end is A, this end is B, and this is theta, and we got this omega. The rod is rotating like this. So omega that we got just before we got omega, square root of 3 G by L 1 minus cos theta. 1 minus cos theta, and this omega is changing with theta. So now we have to find the angular acceleration of the rod. So let me assume that this angular acceleration is, say, alpha, like this. So what I can write alpha? Alpha I can write omega d omega by d theta. Alright. So omega is square root of 3g by L into 1 minus cos theta and d omega by d theta. And d omega by d theta, when I will differentiate, I will take square root of 3g by L outside, and then I will differentiate square root of 1 minus cos theta, and by chain rule I will get 1 upon 2 square root of 1 minus cos theta, and differentiate 1 minus cos theta, that will be just sin theta. So a lot of things will be cancelled. So alpha would be, how much alpha would be, this whole thing, that thing will be cancelled. 3g by L, 3g by L will become 3g by L, and by 2. So this is a 3g by 2L into sin theta. So alpha is continuously increasing with theta. So as it is rotating more and more, alpha is actually increasing. So angular acceleration we got, omega we got. Now velocities of ends A, B and center of rod. So once again, this is end A, this is end B, and here is the IAOR. Here is the IAOR, and if I join this from origin, I mean the intersection point of floor and the wall, so that has to be obviously center. And this is IOR. And from IOR, motion will appear to be pure rotational. So angular velocity we just calculated, omega. And this is theta. The length is L. And this is theta. So this length would be this whole length. This length L, and this theta. So that would be L sin theta. And this will be L cos theta. And this will be L sin theta. Right? So this length is L cos theta, and this is L sin theta. So from here IOR, if I look to the point B, its velocity would be this R into omega. So VB would be L sin theta into omega, like this. And VA will be along the wall, perpendicular to this radius vector from IOR to A, and that is VA. And VA would be L cos theta into omega. And now the center. The center is obviously at a distance L by 2. L by 2 from IOR. So the magnitude of velocity will be, velocity vector of center of mass would be like this, C, VC. So VC would be, how much VC would be? VC is L by 2 omega. In fact, now we can find the velocity of any point of the rod. Okay. So that we got. And then we have to find a point of the rod whose velocity is a long rod. See here. See, this is the rod, and velocity of point A is on this side of the rod, on this side of the rod, and velocity of point B is on the other side of the rod. So clearly one point of the rod, there must be one point of the rod where the velocity vector would be along the rod. And obviously it has to be between A and C, because at C itself velocity has come on the other side. So we want to locate that point. Okay. So for that thing, here again I'll take the use of IAOR, that was A and that is B, and now I'm treating it as a floor as a x-axis and wall as y-axis. So I want to locate the coordinate of that point of the rod where the velocity is along the rod. Again, let me go to the IAOR. This is here IAOR is. This is IAOR. So obviously that point where the velocity is perpendicular to the rod must be, the line joining IAOR to that point must be perpendicular to the rod at that point. How? Because if I draw a perpendicular to the rod like this is a perpendicular to the rod. So suppose this point is say P. If this point is P, so velocity at this point must be IAOR, I want to just write say maybe Q right now. So velocity of point P must be perpendicular to the PQ, and because PQ is perpendicular to rod, so velocity of that point would be along the rod. So if I want to find a point on the rod where the velocity is perpendicular to the rod, so that point should be such that a line joining IAOR to that point must be perpendicular to the rod. So that is the basic thing. Now this is theta, and this length where this, 1 minute, this is L, this is theta, so this is L sine theta. So this is L sine theta, so this is also L sine theta. So this is L sine theta, and this is theta, that is 90 minus theta. This is 90, so that is theta. So from here in the diagram you can see that AP is equal to AP in the right angle triangle. AP would be L sine square theta, L sine theta into sine theta. So AP is equal to L sine theta into sine theta. That is L sine square theta. So now if we got AP, and suppose this AP as a coordinate x comma y, so obviously this length would be, suppose let me join this is say n. So now Pn is equal to AP sine theta. So Pn is AP sine theta, that would be now L sine cube theta. Alright, and now An is equal to AP cos theta, so that would be L sine square theta into cos theta, and this is O. And if coordinates are x, y, so Pn is equal to basically x, and this is y. So x coordinate we got. Y coordinate would be this whole AO. AO is the L. AO is not L. AO is L cos theta. AO is, Y is AO minus AN. So AO is L cos theta minus L sin square theta into cos theta. So I can take L cos theta common, then I will have in the bracket 1 minus sin square theta, that is cos square theta. So that would be L cos cube theta. So I got a very good result. coordinate of that point where the velocity vector is along the rod. So that would be L sine cube theta comma L cos cube theta. 7 part done. Now location of, oh, that was the same thing, we solved it. Equation of trajectory of a center of rod. Okay, and when the rod makes angle theta from vertical. Once again, for the equation of trajectory, my coordinate axes are like this: x-axis along the floor, y-axis along the wall, and origin is the point of their intersection. So here C is the center. Its coordinate is x comma y. If I join here and if I join here, so clearly this x coordinate, see that this and this triangle and this triangle are similar, so this length and this length are equal, and this length is L sine theta, so that is a basically L sine theta by 2, or directly I can write the coordinates. The coordinate of this point would be L sine theta comma 0, and the coordinate of this point would be 0 comma L cos theta. So directly, without any fuss, no need to say all these things, we have 2 points, their coordinates are known, so the coordinates of the midpoint of those 2 points are simply the x1 plus x2 by 2 comma y1 plus y2 by 2. So x coordinate would be 0 plus L sine theta by 2, that is L sine theta by 2, and y coordinate would be L cos theta plus 0 by 2, that is L cos theta by 2. And in fact, in the theta there is a omega. Theta would be omega t plus half alpha t square, so time is there inside theta. To find equation of trajectory, we have to eliminate time term, so we have to eliminate theta term. Simply square and add these two. So squaring and adding, I will get x square plus y square is equal to L by 2 whole square. So that is clearly a circle. The circle center is at the origin, and radius is L by 2. So trajectory of center of the rod is a circle like this. Initially, when the rod was vertical, the center was at L by 2 height from the floor, and when rod lies flat, the center is again at a distance L by 2 from point of intersection of the wall and floor. So it moves in a circle. So that will also be helpful in finding the motion of C. If we know the trajectory, that will be helpful in writing motion of that point. Our trajectory equation is circle. Center's trajectory is circle. Now we want to find the equation of trajectory of a general point. General point means, suppose this is a, this is a B, and say I have a general point, say this P. General point is defined, say that is at a distance x naught from the upper end, and at this position theta I have to write the equation of trajectory. Now, in fact, equation of trajectory is independent of theta, so I am taking a general moment here. So first of all, let me go ahead and that's purely intuitive way. Equation of trajectory of A is a straight line. Equation of trajectory of B is also a straight line. Equation of trajectory of center is a circle. So can we think of a single curve which can be reduced to straight line and circle? So that thing comes to mind as an ellipse. ellipse can be reduced to a circle also. If the A and B, either A or B is made to 0, that will reduce to circle. And if A and B are made to equal, that will become a circle. If either A or B is made to 0, that will reduce to a straight line. And if A and B are made to equal, that will be a circle. So intuitively, I get a feeling that that could be an ellipse. Let's see whether my intuition is correct or not. So let me take the coordinates of P, x, comma, y. So here the x coordinate, this is P, and let me write n. So an is equal, x naught is a fixed thing, x naught is fixed, so an is equal to x naught cos theta. Yes, x naught cos theta, and np is equal to x naught sin theta. Okay, so this is basically x coordinate, np is the x coordinate, so x coordinate I got, so x coordinate is equal to x naught sin theta. So I can write x by x naught is equal to sin theta. And the y coordinate is basically this height. And this height is the y coordinate. This is x, this is y. And this height is basically this height minus this height. This height is L cos theta. This is L and this is L cos theta, and that is x naught cos theta. So y is equal to L minus x naught cos theta. Now directly I could have written from here itself. This is x naught, this is whole thing is L, so that is a L minus x naught, and this is theta, so y is equal to L minus x naught cos theta. So y divided by L minus x naught is cos theta. Now if I square and add these things, this is 1, this is 2, square and add these things, I will get x square by x naught square plus y square divided by L minus x naught whole square, and that is equal to 1. This is ellipse. But that ellipse will be different for different point. Now see. Okay, let me further simplify this also. So I got x square by x naught square plus y square by L minus x naught whole square is equal to 1. And that could be reduced to L minus x naught square x square plus y square into x naught square is equal to L minus x naught whole square into x naught square. I want to avoid the indeterminate form. So now let me check the boundary conditions. So what are the boundary conditions? If the P is my middle point, or rather take the end point. If my point P is at A, so x naught is 0. So here at A, and this is B, x naught is 0 would mean what? X naught 0 means this part will vanish, and no, this part will not vanish. This part will be there, this part will vanish, and this part will vanish, so that will give me x is equal to 0, that is a y-axis. And if I take x naught is equal to L, x naught is equal to L, so this part will vanish and this part will vanish, so that would give me y is equal to 0. Y is equal to 0 mean the x-axis, that is perfectly alright. And if x naught is equal to L by 2, so I'll rather keep this, so that will be simply x square plus y square is equal to L by 2 whole square. So perfectly matched here. So in general, equation of any general point of the rod equation of trajectory of any general point of the rod is an ellipse. All right. Now the real good parts. These were the kind of a sitters. Now the real good thing is when there comes the acceleration. Now acceleration of end B. This was A, this was B. This is theta, and yes, this is 90 degree. This length is L, and this is X, and this has a velocity VB. And let me also assume this has a acceleration AB. So obviously we can write VB is equal to, AB is equal to VB dVB by dx, variable mass, variable acceleration. And this thing I can write VB into dVB by d theta divided by dx by d theta that I want to use. First simple thing. So x, you can see that L sine theta. So dx by d theta is equal to L cos theta. Okay. And VB we had got here, that was omega from here, and it was omega L cos theta. I messed here. Okay, it's good that I come back here. So this is actual. This is L cos theta, and this is L sin theta. VA is equal to L sin theta into omega, and VB is equal to L cos theta into omega. So VB is equal to L cos theta into omega. So now AB, dVB by d theta part. So here if I take L outside and omega is variable, so I will do the product rule. Omega into cos theta derivative is minus sin theta, and plus cos theta into d omega by d theta. And omega we had got 3 G by L 1 minus cos theta. So here L, and inside bracket that is a square root of 3G by L into again in the square root of 1 minus cos theta. I can take it to the next page, that would be better. Alright, so put the value of omega here, that is L. Putting value of omega square root of 3G by L into square root of 1 minus cos theta, and minus sin theta is outside, plus cos theta differentiated by with respect to theta. So first of all we'll have square root of 3G by L, and that thing will be 1 minus cos theta, and this derivative will become sin theta. So of all, I can safely take this square root of 3G by L outside, and also I want to take this square root of 1 minus cos theta also outside. So if I take this outside here, that will become 1 minus cos theta into minus sin theta, and that would be here sine theta, or in fact if I take 2 here, so 2 will come here, sine theta into cos theta. So from here, okay, one more thing that yes, so this would be square root of L into 3g by L by 2 into 1 minus cos theta square root, and also I want to take sine theta also outside. If I take sine theta outside, so now what I will have, 2 cos theta minus 2 and plus cos theta. So I got L by 2 square root of 3g by L sine theta divided by square root of 1 minus cos theta, and that is a 3 cos theta minus 2. Okay. Now we have to find the acceleration of this NB. So we got this. And we had to find the acceleration of NB, which was VB dVB by dx, and that is a VB dVB by d theta dx. So we have to just multiply three things. This term, and this term all together. VB is this, dV by d theta we calculated in the next page, and dx by d theta. So club all those things together. AB theta, and this acceleration is AB. AB got VB dVB by d theta divided by dx by d theta. So AB, VB was, this VB was omega, this length was L cos theta, L cos theta omega. Omega was square root of 3g by L into square root of 1 minus cos theta. And dVB by d theta we calculated here. This is L by 2, be careful, L by 2 square root of 3g by L square root of 3g by L into sine theta divide by square root of 1 minus cos theta into 3 cos theta minus 2. Let me check it. Yes. And dx by d theta is L cos theta. Dx by d theta is L cos theta. Many terms will get cancelled. See. L cos theta. So, AB, you see that this L cos theta and this L cos theta will get cancelled. This square root of 1 minus cos theta, this square root of 1 minus cos theta will get cancelled. This root 3g by L and root 3g by L will become 3g by L. And then there is a L by 2. And then sine theta into 3 cos theta minus 2. So finally, AB we will get 3g by 2 sine theta into 3 cos theta minus 2. And this I will be using for the last part. So let me use it right now. And that itself is a very good question. At what angle the rod will lose contact from wall. So the last part is angle theta when the rod B loses contact. So this is A, this is B, this end acceleration is AB, And suppose we solve acceleration of A as, obviously it will move along this line only. So acceleration of A would be this. So clearly acceleration of center of mass will be, x coordinate of center mass will always be half of the x coordinate of B. So acceleration of center of mass will have a x component as a AB by 2, and acceleration of center mass will have a y component as a AA by 2. If I draw FBD of the rod at this moment, it will have this normal NA, here normal NB, and obviously its weight mg. So when it will lose normal from end A, so when it will lose contact from wall Na is 0. If I want to apply F external along x direction, that will be m into ACM along x. Only force along x direction is Na, and this is obviously theta. So Na and ACMX is AB by 2. So when Na is 0, Na is 0 implies AB is 0, and AB was 3g by 2 sine theta into 3 cos theta minus 2. So obviously this cannot be 0. Initially it was 0. It had no normal. So later only this thing can be 0. So this AB would 0 would mean cos theta is equal to 2 by 3. Mean theta is equal to cos inverse of 2 by 3. Cos inverse of 2 by 3 mean that length. So this length will be 2L by 3. Initially the rod, total length of the rod on the wall was L. Now the length of the rod, projection of the length of the rod on wall is 2L by 3. So the rod has fallen a distance L by 3. So we can also say when the rod has fallen a distance L by 3, at that time the rod will lose contact from wall. So that is in itself a very good part. And acceleration of end A we got and B we got. So now from this acceleration we want to find acceleration of IAOR. Why I want to find acceleration of IAOR is because many people think that AOR has acceleration 0. AOR has not in general acceleration. Sometimes it can have acceleration 0. AIR has a 0 velocity. 0 velocity does not mean 0 acceleration. So here that is a IAOR, and the rod is rotating like this. It has a omega, it has a alpha. So from here if I see from the B, so from here also the sense is like this. So from here omega would be like this and alpha would be like this. And we know that if we know the one point of the rigid body, we can get any acceleration of any other point. So this acceleration we got AB, and this angle is theta. So this length would be L sine theta. So with respect to B, IUR will have a one acceleration, that would be towards B. Path of any particle with respect to any other point is a circle. So in a circular motion there can be two accelerations, centripetal, tangential, and from the ground frame, if we want to find the acceleration, we have to add that acceleration. So this acceleration would be L sine theta into omega square. And for the tangential part, that acceleration would be L sine theta into alpha, and then we have to add the acceleration of AB also. AB we got, alpha we got, omega we got. So we can calculate the acceleration of IOR. And what is interesting, you can check yourself that when we solve the acceleration of IAOR, so what is interesting is that acceleration of IAOR comes out to be towards center always. You can check for yourself, I am just stating it. So acceleration of IOR comes this part, if this length is L by 2, so it will have a resultant acceleration towards center, and that acceleration, this is the acceleration. So this is, I am just writing the direction. So direction of IOR, when you will solve that, that will be towards center. So acceleration of IOR will be directed towards center at all moments, center of the rod. And that would be how much? That would be, if you solve, you will find that would be also very good. That would be L by 2 omega square. So L by 2 omega square. Now the same way from, like I have got the, from acceleration of B, I got acceleration of IOR. Similarly, we can get the acceleration of A also, and the acceleration of the center is the arithmetic mean of acceleration of A and B. So we can get the acceleration of A also. So what is interesting here, there are two very good results are in this question, 3 very good results, that there is a one point whose velocity is along the rod, acceleration of center mass is not 0, and that acceleration is towards the center of the rod, and there is a 1 theta at which the rod will fall, and when the rod will lose contact from the wall, and when the rod loses contact with the wall, the rod falls a distance L by 2. So those are the things. So thank you for watching. It is a long video, but it covers lot of concepts, some easy and some very good. Thank you.